Hello guys, so we will take one more problem on centrifugal pumps here. Okay, the problem number 3. It says the centrifugal pump delivers 50 liters per second against a head of 24 meters. So inevitably the head, whatever is given is the manometric head, and it is 24 meters, and flow rate is given, which is 50 liter per second. So I'll directly convert this into meter cube per second as 0.05 meter cube per second. Next, when running at a speed of 1500 rpm, so n is given as 1500 rpm. Okay, the velocity of flow is maintained constant. That means if the velocity of flow is maintained constant, what you have to take? Vm1 is equal to Vm2, and I guess the value is given as 2.4 meters per second. So Vm1, so this is 2.4 and this is also 2.4 here. Okay, next. And the blades are curved back at 30 degrees to the tangent at the outlet. So whatever the angle is being given here is the outlet blade angle, which is beta 2, which is equal to how much? 30 degrees. So 30 degrees is the angle of outlet blade angle, which is 30 degrees. I will even write it on the velocity triangle as well. Next, the inner diameter is half the outer diameter. So what is this? Inner diameter is half the outlet diameter, he says. That means it is clear that d1 is equal to 0.5 times of d2. Okay, the manometric efficiency is 80%. So I would just take that. Efficiency manometric is 80%. In terms of points, it is 0.8. Okay, so determine the blade angle at the inlet. So what we need to find is the blade angle at the inlet is being questioned, and power required to drive the pump. So power is being questioned. So power is nothing but the work done is questioned. So let us go with the solution of this. The solution. So the velocity triangles are drawn in the same way, assuming it as a backward vane pump. So assuming backward vane pump. So naturally, if it's not given anything, you have to assume it as backward vane pump, and 80% of the problems would be on the backward vane pump as well. So let us go one by one with the calculation. Now, since you know the value of this one, 2.4, we will try to calculate the B1. Okay. The thing given here is if D1 is equals to 0.5 D2, then it clearly implies that U1 must be equal to 0.5s of U2. Okay, because U is pi dn by 60. Since the speed remains same for both the inlet and outlet, only the diameter is varying. So if D1 is 0.5 times of D2, if D1 is 0.5 times of D2, then U1 would be equal to 0.5 times of U2 as well. Okay, and how to find out D1? So you can use the you have to find what is D1 now. So how do you find it? So you can use the manometric efficiency. So manometric efficiency is manometric head divided by Euler's head, or Euler's head is equal to manometric head divided by manometric efficiency. So that is equal to 24 divided by 0.8, that is equal to 30 meters per second. So this is this is meter, not meters per second. It is the Euler's head. Now we know that Euler's head is given by, that is Euler's head HE is given by U2 VU2 divided by G, where G is 9.81. So G is 9.81. So just keep it aside. We will come one by one. So if you find the value of VU2, you can calculate this. So from triangle ODE. So now you are in the race to calculate what is VU2. Can I apply tan beta 2? That would be equal to Vm2 divided by U2 minus of Vu2. So U2 minus of Vu2 is nothing but Vm2 divided by tan beta 2. Now, so from this Vu2 is equal to U2 minus of Vm2 divided by tan of beta 2. So Vu2 is equal to U2 minus of Vm2 is how much? Vm2 is 2.4. I will take that. So it is 2.4 minus tan of beta 2 value is 30 degrees. So that is equal to U2 minus of 4.157. This is Vu2. Okay, so now I would take this as equation number 1. So from 1, okay, from 1, what I have is HE is equal to U2 Vu2 divided by G. So that is equal to U2 into U2 minus of 4.157 divided by G. G is again, I will directly write it as 9.81. So when you solve this, in terms of quadratic equation, and HE value is 30 meters. So this is equal to 30. When you solve the above quadratic equation, you will get as U2 square minus 4.157 U2 minus 294.3 is equal to 0. When you cross multiply all this stuff, you will get this quadratic equation, and you can solve this directly by using the calculator. You will get the value of U2 to be 19.36 meters per second, and this is the value of U2 you are going to get. So I'll immediately substitute there as well. So U2 is equals to 19.36. Okay. Now, once you've got the U2 value, you can even calculate the U1 value. So U1 is equal to what? 0.5 times of U2. So this is 0.5 times of 19.36. So that is equal to 9.68 meters per second. So this is 9.68 U1. I'll just write it as 9.68. Now you got the value of Vm1 was already given. U1 you have calculated. Now you can calculate what is inlet bleed angle, beta 1. So applying tan there. So tan of beta 1 is equal to, opposite was Vm1 divided by U1. So beta 1 is equal to tan inverse of Vm1 by U1. So that is equal to tan inverse of Vm1 is how much? 2.4 divided by 9.68. So beta 1 would be equal to, when you calculate that, you will get it around 13.9 degrees. Next, we have to calculate power required to drive this pump. So power required is nothing but the work done, and the work done or power is given by rho kef U2 Vu2 watts. So all the quantities are there. you can just calculate the things up there. Okay, U2 you can calculate using that particular expression here. You can pick this one to calculate your VU2. Okay, VU2 is U2 minus of 4.157. So U2 is how much? U2 is 9.68 minus of 4.157, and this is 15.2 is the value VU2. So now substitute all the values to get the value of power. P is equals to 1000 cross 0.05 cross 19.36 cross 15.2. So the power required is 14.71 into 10 to the power of 3 watts, which is equal to 14.71 kilowatts. Okay.